You are looking at an animal with 3 hearts beating inside its body right now. Not 1, 3. And here is the strange part. When this creature swims, one of those hearts stops. It just shuts off. You would think that sounds like a malfunction. It is not. It is one of the most elegant survival trade-offs in the animal kingdom. And it explains almost everything strange about how an octopus lives, hunts, and moves through the ocean. The animal is the octopus, and the real answer to why it needs 3 hearts is far stranger than simple redundancy. Start with the basics. Most animals you know, including you, run on 1 heart and red blood. Your blood is red because it carries oxygen using a molecule called hemoglobin, which is built around iron. An octopus does not use hemoglobin. Its blood runs on a molecule called hemocyanin, built around copper instead of iron. That is why an octopus bleeds blue, not red. Why does that matter? Copper-based blood is much worse at carrying oxygen than iron-based blood. Hemocyanin floats loosely in the blood plasma instead of packing into blood cells the way hemoglobin does in you. It is a simpler, older system, left over from the octopus's molluscan ancestors, and it moves oxygen far less efficiently. So the octopus inherited a transport system that is, frankly, not built for a fast-moving, high-energy predator. And that is a problem, because an octopus is exactly that. It has to move fast enough to catch crabs and fish. It has to power a soft body with no skeleton, squeezing muscle in every direction at once. It has to run a brain so complex that roughly 2/3 of its neurons sit not in its head, but scattered through its 8 arms. All of that costs oxygen, a lot of it. So evolution needed a workaround. And the workaround was not better blood, it was more pumps. 2 of the octopus's hearts are called branchial hearts, one positioned beside each of its 2 gills. Their only job is local. Each branchial heart takes in low oxygen blood returning from the body and pushes it directly through its own gill, forcing as much oxygen as possible into that slow, copper-based blood before sending it onward. Think of them as dedicated boosters, 1 per lung, working purely to compensate for how inefficient the blood already is. The 3rd heart is the systemic heart. This is the one you would recognize as a heart in the traditional sense. Positioned centrally, it takes the freshly oxygenated blue blood arriving from both gill circuits and pumps it out to the rest of the body. The arms, the organs, the brain, the skin that can shift color in a fraction of a second. 3 hearts, 3 separate jobs, working as a relay system to move oxygen through a body that never evolved efficient blood in the first place. Here is where it gets counterintuitive. The systemic heart, the main one, struggles under exertion. When an octopus jets through open water using its siphon for propulsion, that systemic heart actually stops beating. Not slows down, stops. This was documented in detailed physiological studies of octopus circulation, including landmark work by the British zoologist Martin Wells, who spent decades studying cephalopod hearts at the University of Cambridge and publishing his findings in journals including the Journal of Experimental Biology. Wells recorded that jet-propelled swimming compresses the octopus's body in a way that physically interferes with the systemic heart's rhythm, causing it to pause during active bursts of swimming. Picture that. The animal's main heart shuts off precisely during the moment it needs oxygen the most. Why would an animal evolve a system that punishes it for swimming? Because for an octopus, swimming was never supposed to be the main event. Its whole body plan is built around crawling. An octopus is, at its core, a bottom dweller. It uses its arms, lined with hundreds of independently controlled suckers, to pull itself along rock, coral, and sand, exploring crevices, manipulating shells, solving problems most invertebrates could never attempt. Crawling is efficient. Crawling does not overload the circulatory system. Jet swimming is a last resort, an emergency escape mechanism, not a daily commute. This is why an octopus that has just jetted away from a predator often looks exhausted afterward, moving sluggishly, retreating to a den to recover. It is not being dramatic. Its systemic heart just paused mid-emergency, and its whole body ran on borrowed oxygen for those few seconds of open water sprinting. Swimming, for an octopus, is not simply moving. It is a physiological gamble. There is a deeper evolutionary story here too. Octopuses descend from mollusks, the same broad ancestral group that gave rise to snails and clams, animals that generally do not need much oxygen and do not move quickly. Most mollusks get by just fine with an open circulatory system, where blood sloshes loosely through body cavities instead of being tightly confined to vessels. But somewhere in cephalopod history, the ancestors of octopuses and squid began evolving towards speed, intelligence, and predation. That shift demanded a far more oxygen-hungry lifestyle than a snail ever needed. Rather than throwing out the ancestral hemocyanin blood chemistry and starting over, evolution did what it usually does. It adapted the existing machinery. It closed off much of the circulatory system into actual vessels, added extra pumping stations at the gills, and built a body plan that leans heavily on efficient crawling over costly swimming. 3 hearts is not a sign of superior design. It is a patch, a brilliant, layered patch, built on top of an ancient, imperfect starting material. There is a modern twist to this story too, and it is one marine biologists are watching closely. Because hemocyanin is so much less efficient at binding oxygen in warmer water, rising ocean temperatures put additional strain on an already stretched circulatory system. Research on cephalopod physiology has increasingly pointed to warming seas as a growing challenge for octopuses, compounding a cardiovascular setup that was already working near its limits, even in cooler, oxygen-richer water. An animal balancing 3 hearts against 1 mediocre blood pigment has very little room for extra stress. So the next time you watch footage of an octopus gliding elegantly through open water, remember what is actually happening beneath that skin. 1 heart has gone silent. 2 smaller hearts are working overtime at the gills, trying to force enough oxygen into a blood chemistry that was never built for speed. The whole animal is essentially sprinting on a system it can barely afford to run. And yet it does it anyway. It escapes predators. It hunts in the open when it has to. It has built one of the most complex nervous systems outside the vertebrate world, using blood that carries less oxygen than a jellyfish's version might, if jellyfish carried any at all. That is the real story behind the 3 hearts. Not brute redundancy, but constraint turned into ingenuity. A body inherited from slow-moving ancestors, pushed by evolution into becoming one of the ocean's smartest hunters, held together by a circulatory system that quite literally has to stop to keep going. Look at an octopus again, and you are not just looking at a strange, boneless animal with too many arms. You are looking at 3 hearts negotiating a compromise that has kept this creature alive for millions of years, one pause at a time.